Hello, welcome to our 11th set of college algebra notes. We are on our last outcome for Unit 1, so this is the last set of notes we'll have before our first unit test. So you should be getting ready for that Unit 1 test. There's practice exams in my math lab. There's a paper and pencil practice exam that has both a multiple choice portion and a short answer portion, similar to what you'll see on the actual exam. The practice exam is a bit longer. The real exam is going to be 5 short answer questions and 16 multiple choice. So it won't be as long as that practice exam. We should be able to get it done in an hour, hour and a half. That's kind of the target time frame for it. Some students take a little bit longer, and that's fine. Okay, but this outcome 11, we're going to deal with some functions and some of the things we can do with functions, including shifting them, translating, reflecting them, where we flip them over, stretching, and shrinking. These are all different things we could do with a function. Now, before I get into using those different operations, first off, just want to remind ourselves of some of the common functions we've seen so far. We've seen things like the constant function. Constant function is anytime you have f of x or y equals some number c, so it's going to be some actual number. Here it's like y equals 1.5 or 1.7 or something like that. And it just gives you a horizontal line. So that will happen anytime you have just the function equals just a plain number, a constant number. You get a horizontal line function. That's a zero slope situation. We have the identity function. Identity function is just a y equals x or f of x equals x. This is kind of the basic version of all those diagonal line functions. You could take this function, kind of stretch, shrink, flip it over, and make all those other straight line functions we dealt with. Your absolute value function, so this is where your function has an absolute value in it, makes this V shape because all the negatives get turned into positives. That's why it looks different than this one. So any kind of absolute value function starts kind of looking like this, and you can transformations. So you can take these basic functions and you can do transformations and get other functions from them. So some of the other ones that maybe haven't seen so much yet, but we'll see later on. The quadratic function, so just the standard quadratic function, this is going to be this x squared, so it's something with an x squared in it. It'll look like this. We'll see a lot more about quadratics in Unit 2. That's the most a lot more time on. The square root function, so instead of a square power, it'll have a square root. Remember, square power, square root, that just means second power or second root. Remember that this root by default is always the second root, so what times itself gives you that number. And that's the square root function. It looks like this. You don't have anything on the negative side because square roots you can't square to negative. So that's why it starts at 0, because the smallest thing you can square to 0, because 0 times 0 is 0. We have a cubing function. Cubing just means a third power. So this one has x to the third in it. So you have x to the third, it'll look like this shape. And then we have a cube root function. A cube root function has a cube root instead of a square root. So now instead of saying what times itself, just 2 times, you say what times itself times itself, so 3 times will give you the value. So like the cube root of 8 would be 2, because 2 times 2 times 2 is 8. And so those would be the cubic and cube root function. We'll see a little bit more of those later on in the semester. But all of these functions I just showed you, including this last one in the bottom corner, are going to be functions we can use in this section to do our transformations with. So these are just some examples. So this one is called the reciprocal function. And it's where you have 1 over x. So you can put f of x equal to y equals 1 over x. And so this is a function where the x is on the bottom. And it looks like this shape. So those are kind of your standard, typical 8 different really common functions. We've seen some of them already. We'll see pretty much all of them throughout this course. With each of these functions, we'll be trying to do things like translations, reflections, and stretching and shrinking. And we'll be doing these both in the vertical direction, so up and down, and the horizontal direction, so left and right. So we have to be careful. Are we doing this, vertical, up and down, or are we doing this horizontal, left and right? And how we determine which one of these we do, whether we're doing vertical things or horizontal things, depends a lot on where we add numbers into the function's equation. We're gonna add values with multiplication, addition, subtraction. We're gonna throw numbers in there, and those things are gonna change this. We're gonna do vertical things or horizontal things. But the location where we add that's gonna matter. So that's why we're gonna define what we call inside and outside. So I'm gonna say inside, I'll have to try to do red, green, and outside I'll do red. So if I take a function, so it's a standard type of function. Let's say, let's do the square root of x. That's an easy function to think about inside. So inside, a function that has a square root function like this, Inside is going to be anything that's inside the square root. So if I want to do something inside, I might do something like take square root of x and add 2 to it. So by putting that plus 2 inside the root, this is going to be inside. So I've affected the function by putting something on the inside. And that's going to be different than if I took this function and I did square root of x plus 2. I just put a little line there to make sure you know it stops here, because this plus 2 is outside the square root. That would be outside. So stuff you do on the outside is not going to do the same thing that stuff you do on the inside. So adding 2 inside the square root is going to be different than adding 2 on the outside. And we'll talk about what that does later, but just kind of, I want to get that as an idea. So if you look at your function, whatever function you start with, you can think about where inside and outside is, always by thinking about where the x is. So in this one, the x is inside the square root symbol. So anything inside the square root symbol is also on the inside. Anything on the outside is outside. Some of these are easier, like the square root is probably one of the easiest ones to see that with. One of the harder ones is probably just the x squared function. So that one, how do you make it inside? Well, to make it inside, you actually have to make an inside. You have to take and put a parentheses, and then I'm going to put my x plus 2. I'm just using the same number, but put it inside and put the power on the outside here, so that all the stuff in the inside is getting that power too. So I got to think of this as the inside now, because everything inside that parentheses has that power. So since there was a power in the original equation, inside is going to be anything that also gets that power, as well as the x. You know, the x got the square power, so then now the 2 also gets the x squared power, so now it's on the inside. You know, if I want to do something outside, I would just leave the x squared as it is, and I put a plus 2 on the outside, and now this plus 2 doesn't have the power, right? It doesn't have a power on it, it's just a plain plus 2, and so that would be an outside. One of the weirdest ones to think about the inside-outside is probably this reciprocal function. Reciprocal function, when you have 1 over x, so when you have the 1 over x function, to do inside is actually be the bottom of the fraction, because that's where the x is. So the inside, I'd do something like 1 over x plus 2, where I put that on the inside of the function on the bottom, and that would be inside. Got to be really careful when you type this one in the calculator, because it's easy to type it like this, like 1 divided by x plus 2, and not put any parentheses, and calculator will do it wrong, because they'll do the division before it does the addition, and we all know that when you have a division bar like this, you want the addition to happen first. So if you type this in the calculator, remember there's an implied parentheses there, so you make sure that the plus happens before the division. You know, we all know it when we look at the paper, but when you type in the calculator will get confused because it doesn't have a division bar, it just has a plain old division symbol. You type that division button, and it's just going to think regular division, it's not going to think division bar. If I want to do something on the outside of this one, outside would be like 1 over x plus 2. And so now that plus 2 is not in the bottom of the fraction, so that's outside. That would not be something on the inside. So these are the big difference. You got to think about whether you're working on the inside or you're working on the outside. Where you work, inside versus outside, changes what you're doing. So adding 2 on the inside versus adding 2 on the outside, it's going to be different. And I did this with plus 2 every time, but I could have used anything. And multiplying, subtracting, I just use plus 2 every time just to kind of show where I put the plus 2 matters, whether it's inside or outside. Is it inside where the x is, or is it outside of the part? Okay, so let's look at the different things we can do. The first thing we're going to talk about is vertical translations. Vertical translations, we're moving stuff up and down. So that's what vertical translations mean. So we're going to be shifting it up and down. So translation is the fancy word. I'll call it shift all the time because to me that's just a little bit smaller, easier word. But it's literally just moving it up or moving it down. Now we can go either direction, right? We can go up or down. So you have to pay attention, which way are we going? Now if we put it on the, if we want to do it vertical shift up or down, if we add a number on the outside, it's going to move it vertically upwards. So it's going to shift it upwards. If we subtract on the outside, we're just going to move it vertically downwards. The amount it moves is just what number you put in there. So the number you add in there, positive, that's how far it goes up, or how far it goes down, just depending on what that number is. And we look at the C has to be a positive. So adding a negative isn't going to move up. You know, adding a negative, same thing as subtracting, that would go down. So if you add a positive, you go up. If you subtract a positive, you go down. You know, if you add a negative, we'll just think of that as subtracting. Okay, so this is what happens. Adding on the outside is upwards, subtracting on the outside is downwards. Vertical stuff is always going to be outside. So to do things or do anything else vertically, if you want to do things up and down, it's always outside. So this vertical is always outside. And that's something important to remember because it's true for all the different transformations we'll do. So for shifts, yes, it's true, but for anything else, it's true. If you do stuff on the outside of the function, put it on the outside, it's going to be a vertical thing. Adding shifts it up, and subtracting shifts it down. So if I want to move it up, I add some amount, and it takes my function and moves it up. So it just takes the whole thing and it moves it up by that far. If I want to shift it down, I subtract, and it takes the whole function and it moves it down that far. So that's how I can move it down. So you just take any function, just throw on a +2 at the outside, and the whole thing moves up. You put a -2 on the outside, whole thing moves down. Pretty easy to move functions up and down. So a couple little short questions, kind of what you see in the homework. So first off, I have y equals g of x plus 3. How is that different from g of x? Well, because we added 3. So we add 3 outside because that's what we did. It's going to shift it. Because it's positive, it's going to go up by 3. Examples of this. So what would this look like? Well, it's like you have the square root of x function and you just put a +3 on the outside. Now it's moved up. That'd be an example. You could have the x squared function and just +3 on the outside. We said they have the identity function where it was just like y equals x. We just take that and you add 3, and again, that's going to move it up. Any function, the 1/x function. Add 3 on the outside. All these are going to be situations where you just took the original function, the basic function we had on that first page, whatever it looked like, square root function, identity function, and the whole function has moved up 3. That's what that would look like. Next one. The graph of y equals square root of x minus 2 is obtained by doing what of the graph of y equals square root of x? So we started with square root of x. You look at this, of course, the thing you're always looking for these is what's the difference? What's changed? Well, in the change here, is they put in a -2, right? That's the difference. You put in that -2. Well, we said before, minus always moves it down. So this is going to shift it down, because when you minus a number, you shift it down. And the number you subtract is how far. So we shift it down by 2. So this just takes this function, takes the square root of x function, and shifts it down by 2. That's what this is doing, because it's a -2 and it's on the outside. So it's outside and subtraction. So that's how we know it's a vertical shift down 2. Because it's on the outside, it's subtraction by 2. And so that's where we go down 2. Because subtraction goes down, outside's vertical, and 2 is how far we go. Okay, that's our first type of transformation. So vertical translation, so going up or down, you're just adding, subtracting on the outside. Well, what if instead of adding, subtracting on the outside, what if we add or subtract inside the function? Well, then we're going to have a horizontal translation. So instead of vertical, we're going to have a horizontal. That's the difference here, is now we're doing a horizontal. Horizontal means, again, that we're going left or right. So this is left or right. This is a horizontal. And the horizontal is going to come from when we work on the inside. So always inside if you want to do a horizontal. So if you want to move it left or right, you're going to do stuff to the inside of the function. So first off, if I want to move it left, so I want to go to the left, the negative direction, I'm going to actually add a number. And this feels backwards to me always. You'll notice that when you're adding a number, instead of going to the right, because if you're adding and going up, you're actually going to add a number and you're going to go to the left. It's going to move it to the left. That's what adding numbers. So this horizontal stuff, you kind of find out that as we go, horizontal always kind of feels a little bit backwards. Adding shifts it left that far. Again, the big thing is that it shifts it left. If you subtract instead, so now if you subtract a number instead of adding, then you move it to the right. So subtraction actually moves it to the right. Pushes it over to the right. And again, that feels backwards, because if I subtract, well, why would I go in the positive direction? Well, horizontal, that's the way it works. Horizontal is always backwards. So subtraction shifts it right by that many units. So when I think about the horizontal, it's in the inside, it feels backwards. You know, it kind of goes backwards of what you expect. Adding a number takes you to the left, subtracting a number takes you to the right. Not kind of what you expect. Okay, so when you get an equation like y equals h of x minus 5, so again, you can see here that this is horizontal because the minus 5 is inside the function. You remember when we would define functions like h of x, and we say, okay, h is the label, x is the input, the inside. So we put negative 5 inside, we put the negative 5 inside the function. So that's going to be inside, and that's because it's a subtraction going to shift it to the right. So this is a subtraction inside the function by 5. So it's going to shift it right by 5. So whatever function it was, it's going to take the whole thing and move the whole function over to the right. So for example, if you had, for examples, you had square root of x. Well, if you take that and you put in x minus 5, then that's going to be that square root function shifted to the right 5. So it's going to be the square root function, but just take the whole thing and move it to the 5 over to the right. So it won't start at 0, it'd start over at 5. Or you could have, the x squared function where you have x minus 5, that squared. This is why last section we covered, we talked about the functions and the symmetry, how you have to have that horizontal symmetry, we fold it side to side, and we saw that when we had numbers inside the power of the square, that they mess stuff up. It's because what it does is it actually takes the whole function and shifts it to the right or the left. It shifts it away from the middle. And if you're not centered, then you don't have a horizontal flip. If I take this square root function, it doesn't have a horizontal flip. And maybe if I take the squared function, x squared function, I shift it to the right 5, then it's no longer going to be centered on this line, and it won't have a horizontal flip over the middle, so it won't be symmetric anymore. So that's actually what was happening with the symmetries, is the minus 5 inside of here shifts it so far off the middle that it's not centered and it doesn't have a symmetry anymore. So you can always kind of watch for these things inside the squared, or if you had like an absolute value, x minus 5, stuff like that, it's not going to be symmetric anymore because that minus or plus a number would shift it horizontally, it would lose its symmetry. These will all be shifted to the right. Even if you had the 1 over x minus 5. Remember, this is inside, so it has to be down where the power is. That would be the reciprocal function, this 1 over x function. Everything moved over to the right 5. So just take this function and shift it to the right. That's what this subtract 5 on the inside does. So it's just going to look like one of these. That's what it's going to look like. Okay, we have the graph of y equals x plus 6 cubed is obtained by doing what to the graph of y equals x cubed? By how much? Well, since this originally starts with x cubed, the only thing that's changed is this plus 6. And a plus 6 in this case is on the inside, so it's actually going to be a horizontal shift left, because we said addition actually goes to the left. That's the weird thing without the horizontal. So this is adding inside. So it's going to shift left. So it shifts left because it's adding on the inside. And because it's adding 6, so adding inside by 6, it's going to shift left by 6. That's how much. It's going to go to the left 6. So again, we're looking where it is. It's on the inside of the function. It's inside the power. So just like the x is getting the power, the 6 is getting the power as well. It's applying to everything inside the parentheses. And so it shifts it left because it's inside. Adding on the inside always goes left, backwards. And then the 6, because we added 6, that's how far we go. So this would take this cubing function that we had, it would have looked like this originally, but adding that 6 in there is going to take this whole thing and move it to the left 6 spots. That's what that would do. Okay, that's the first type of transformations are all translations. So we had vertical translations, and we had horizontal translations. The next type of translation is going to be reflections. So reflections is where we're going to flip it, and we're always going to flip over one of the axes, right? We're going to flip over the x-axis or the y-axis. I'm going to think of the first one, where we flip over the x-axis, remember that's going to flip this way, is a vertical flip. So the first one, we're going to call this a vertical flip. So we'll say this is vertical flip, because we're flipping up and down. So that if you flip over the x-axis, the vertical flip. And to do this, what you'll see is that the function has a negative in front of it. It's like you take the function and multiply it by -1. So if your function originally was like x squared, you put a negative in front of that. So you have negative in front of the x squared. Or if you had an absolute value of x, you put a negative in front of the absolute value. That negative in front is going to reflect it Over the x-axis, it's going to be a vertical flip. That's what we'll call this. Now the other option here is kind of flip it over the y-axis. Well, we flip over the y-axis, we're going to flip horizontally because we're flipping this direction. If we're flipping over the y-axis, we're flipping across the y-axis. That is going to be a horizontal flip because we're flipping horizontally over the y-axis. So we'll call this one a horizontal flip. Your book doesn't really call them horizontal and vertical flips, but I like the fact that they kind of match up. Your book will always refer to the axes, which is a good thing to remember because it's good to remember that they always flip over the axes. They don't just flip willy-nilly. They always have to flip over an axis, so you always have to look at that. But I like to think about this when y-axis is flipping as horizontal flips and vertical flips for the x-axis. So horizontal flip is what happens when we do the y-axis. We flip horizontally because we put the negative on the inside. Again, inside is going to work horizontally. Outside is going to work vertically. Now, the nice stuff is that it's consistent. It works the same way it's been the whole time. Okay, so we're going to take this function. This is g of x right here. So this is the function g of x. And we're going to find both negative g of x and g of negative x, which means, of course, negative on the outside is going to be a vertical flip. It would be a vertical flip. And negative on the inside is going to be our horizontal flip. So again, negative on the outside, it's going to flip it up and down over the x-axis. Negative on the inside, it's going to flip it side to side over the y-axis. So we're going to take this function, we're going to do that. Now, on your homework, when you're doing MyLab and stuff, and if you're doing test questions, you'll typically either get to pick the right graph out of multiple graphs, or you just tell MyMathLab what to do. You'll say, okay, I see a negative on the outside, you need to do a vertical flip. Me, I don't have MyLab, I just have a paper, so I get to do this by hand. So when I'm doing this by hand, one thing I do is I label some points on my graph. So I'm going to start with my graph and say, okay, right here you can see a 0. So this point right here is going to be 0, 1, because that's that point. This is the middle 0, 0, that's 0, 1. Over here we have the point 1, negative 1. So 1, negative 1 is the point right there. If I go over here, 2, 1, this point would be the point 2, 1. And that'll just give me some points so that when I go to flip these, when I go to flip it horizontally, vertically, I kind of know where to put my points because I know where they start out. So that's why I labeled those. You're not going to really have to worry about that with your homework. Okay, so first off, I want to do a negative on the outside, which is my vertical flip. So this is my vertical flip, which means I'm flipping over the x-axis. I'm flipping up and down. That's because of the negative on the outside. So points like 0, 1, instead of being, where they were, it's going to flip over this axis. So instead of being 1 up, it's going to be 1 down. It's going to be down here. It's going to be the point 0, negative 1, because it's going to be down instead of up. This point here, I have a 1, negative 1. Well, instead of being down here at 1, negative 1, it's going to be flipped up to point up here to 1, positive 1. Last point I have at 2, 1. Well, instead of being 2, 1 up here, it's going to flip over, be down here at 2, negative 1. So notice what I actually did to get this is every time I just took the y value and changed the sign on the y value. If it was positive, I changed it to a negative. If it was negative, I changed it to a positive. Because by changing the sign on the y values, you flip the graph over, and so now it looks like this. And again, this isn't perfect, I'm drawing it by hand, but you get the idea. It should look like that graph, only flipped upside down. I made mine a little bit long because I just extended the lines longer. So it's kind of the same idea, but it's flipped over this x-axis. Again, we're flipping over that axis. We're flipping over this x-axis. That's what we flipped over. So that's why some of it ended up on top because it used to be below. Some of it ended up on bottom because it used to be above. Okay, let's take the same graph now, though. Let's do the other. Let's do the horizontal flip. This time, again, we're flipping over the y-axis. So we're flipping this way, side to side. And it's because there's a negative on the inside. So I'm going to take points like 0, 1. I'm going to look at 0, 1 straight here and say 0, 1, when you flip it horizontally, well, it's right on the axis, so it doesn't go anywhere. It's right in the middle, so it stays in the middle. So that 0, 1 is still 0, 1. My next point, I have 1, negative 1 right here. But again, flip it horizontally over this axis. So I flip it over this axis. So negative 1, negative 1 flips over to become negative 1, negative 1. So it flipped over horizontally. Last point, I have 2, 1 up here. So 2, 1 would have been here. But it flips over. Since it's 2 away, it's going to actually end up 2 to the left. So it flip over all the way over here. So it's become negative 2, 1. So that 2, 1 become a negative 2, 1. This time, you notice that it's the x values that the sign changed, right? My positive 2 became a negative 2. My positive 1 became a negative 1. 0, of course, doesn't change because his negative 0 is the same thing as regular 0. That's why that one didn't move at all. If you're in the middle, then your flip doesn't really do anything. But that ends up with a graph that looks like this. It's not flipped upside down, it's just flipped horizontally. So it got flipped over this y-axis. So you can see how it was like this, but now it's going the other way. It got flipped over. So it's a horizontal flip. So again, if there's a negative on the outside, it's a vertical flip. If the negative's on the inside, it's a horizontal flip. So negatives always flip it. A negative flips it, but the direction it flips depends on where the negative is located. It's on the outside or the inside. Okay, that was the second type, major type. Both vertical and horizontal reflections. They're all reflections. They all come from negatives. We saw translations came from adding and subtracting. These shifts came from adding and subtracting. Negatives do this. Well, the last thing we need to do is shrinks and stretches, and those both all come from multiplying. These are also going to be in 2 separate pages because first off we'll deal with vertical. So if I want to vertically stretch and shrink, so if I'm looking at vertical stretches and shrinks, I'm going to multiply. So you do this by multiplying. So you multiply, and because it's vertical, like we said before, vertical is always on the outside. Now the numbers you're going to multiply are always going to be bigger than 0. You're never going to be dealing with negatives because the negative, we already saw what the negative does. The negative does the flips, the reflections. So when we look at stretches and shrinks, we never look at the sign because the negative is actually doing the reflections. That's a whole separate thing. In this case, when we're looking for stretch shrink, we just look at the number by itself. We ignore the negative. If the number by itself, without the negative, if it's bigger than 1, so if the number is bigger than 1, it is going to take the graph and it is going to stretch it, which makes sense, right? You multiply by a big number, anything bigger than 1 is big, right? Because if you multiply by 2, 2 is bigger than 1, well, then things get twice as big. If you multiply by 1.5, that's going to make things 1.5 times bigger. So any big number, 5, 10, a million, all those would just make it bigger. If you multiply on the outside, you vertically stretch it. And you can find out how you do that by multiplying all of its y values, y coordinates, remember, are the heights, by that value. So if you want to like double it, so you multiply by 2, then you take all the y coordinates for the points, the y values for the points, and just double them, multiply them by 2, and that's what the new graph will look like. Now the other option is to multiply by a number less than 1. And why are things less than 1 important? Well, less than 1 is going to be numbers like a half, or 2/3, or 3/4. All those numbers are small enough that if you multiply by those numbers, things get smaller. I know that feels weird because you think multiplication, you think numbers get bigger. But we all know that if I take my money and I multiply it by half, so I have half as much money, I have less money, right? I don't have more, I have less. If I have 2/3 of the money I used to have, I have less money. So when you multiply by a fraction smaller than 1, you get smaller numbers. So if you multiply by a number smaller than 1, what happens is you actually vertically shrink. You shrink the graph if you multiply by some number smaller than 1. Remember, we're not going to start with negatives. That's what I'm thinking, things between 0 and 1. So like, fractions between 0 and 1, decimals between 0 and 1. Because again, we're not going to look at negatives because negatives, we always use the negative for the reflection. We're just looking at the number without the sign. And you can figure out how to shrink it by multiplying all of the y coordinates by that value. So if you're multiplying everything by half to make it half as big, to shrink it by half, you could just take all the y values, the heights for all your points, and multiply them by half and get that. Now again, you're not going to have to do that because my algebra is pretty friendly, and so it'll just say, okay, tell us what stretching or shrinking occurred. You can't do both, right? Because you need to multiply by a big number or a small number. You can't do both at the same time. So you just look at the number and say, oh, it's a big number, so it gets bigger. It stretches by this much. Or it's a small number, less than 1, and it shrinks by this much. So again, shrinking because it's between 0 and 1. So this one we multiply by c, and it gives us this smaller thing that's not as tall, it's not as extreme. It shrunk it down. Multiplying by a number bigger than 1, it's going to make it bigger, so it's going to stretch it out, and it's going to make it taller. So that's what happens. The bigger number stretches out, makes it taller. The small number shrinks it down, makes it shorter. So let's look at a function and then see what happens. We're going to take this function, we're going to multiply by half. Because we're multiplying by half, that is a small number. we do expect it to shrink. And again, this is on the outside, right? So it's outside the function. So if it's outside, we expect it to vertically shrink because outside multiplication shrinks it vertically. Okay, so I'm going to take this function I originally have here that has points. I'm just going to use my points. Again, I got to do this by hand. On your homework, you just tell it that, oh yeah, it shrunk by 1/2, and that's pretty much all you have to do. So I'm going to look at this and say I got 0.11, I got a 0.00, a point -1, -1, and kind of point -2, -2. So those are the 4 points on that line. And each one of these, to get the vertically shrunk version, I'm going to take the y value and multiply it by 1/2, or take 1/2 of that. So to shrink this first number, that -2 is going to become -1, because 1/2 of 2 is 1. So I'm going to go -2 to the left, but I'm only going to go -1 down. So that point goes to -2, -1. So it's half as big. It's not as far down. Next point, -1, -1. Well, I'm going to go -1 to the left, but I'm only going to go half as far. So 1/2 of 1 is 1/2. So that point becomes -1, -1/2. 0, well, 1/2 of 0 is still 0. So that one just stays where it is. That one does not change. That's going to be 0, 0 still, because 1/2 of 0 does not change. So values that are on the x-axis, when you shrink, they will just stay on the x-axis. Everything's getting closer to the x-axis. Well, if you're already there, you can't get any closer, so you just stay there. Last one, 1, 1. So instead of being 1, 1, I'm going to go half as high. So it's going to be right here at 1/2. That's what that is. So it's going to look like this. It's going to be a line. You'll notice this line is literally half as tall. This line used to be 1, 2, 3 from the top to the bottom. So 1, 2, 3. This line you go up 1.5 or 1.5 is half of 3, right? So this is half as tall. So this distance here is 1.5 versus this distance here, this length here, is 3. So it is half as tall. Now, when we deal with real lines or typical lines that go up and down forever, the graphs we see most of the time, go up and down forever, like that, they kind of reach up and down forever. Half as tall is not really that big a deal, because when you're infinitely long, half infinity is still infinity. But what you should notice is that even if you if you have a line that goes infinitely long, doesn't get shorter, it does get flatter. So when you shrink it down by half, you actually make the line flatter. It's not as steep. So doing that actually reduces the slope, which makes sense, because remember, slope is the number in front of your x. If you multiply everything by half, you actually make that slope number half. You make it smaller, closer to 0 slope, so it makes it flatter. So if you multiply everything by a big number, you'd actually make it steeper, and you make it taller. So you make it so it climbs up faster if you multiply by a big number, because it'd be increasing the slope, basically. Okay, that was vertical, because we multiplied on the outside. So now let's do horizontal. Now horizontal again, horizontal, stretching and shrinking, is still multiplication, but the location you multiply is different. So instead of multiplying the outside, we're going to multiply inside. Big surprise, right? Everything we've done so far that's been horizontal has been on the inside. So now we're going to look at stuff, we're going to do inside stuff. Now if I use a number bigger than 1, so I'm looking at something bigger than 1, I'm going to multiply on the inside, so it's going to be inside my function, but it's actually going to horizontally shrink it. So this stuff, again, still feels backwards. This horizontal stuff always feels backwards. The only thing that doesn't feel backwards is the flips, and that's because flipping one way versus the other way doesn't really matter, so there is no backwards. But when you're doing the shifts or the stretch shrink, horizontal always feels backwards, because when you use a big number, bigger than 1, instead of getting bigger, wider, it gets thinner, it gets smaller. So multiplying by a big number takes your function and makes it smaller horizontally. It's not as wide. If, however, you use a small number, so now instead of using a big number, you use a small number, and you multiply by a small number, something less than 1, remember small is smaller than 1, then it is horizontally stretched. You can do that by dividing every coordinate by c. I forgot to mention on the first one too. You can actually figure out how this works if you take all the x values and divide it by that number. Since you want to shrink, you want to do the opposite. If you divide by a big number, it's going to get smaller. If you divide by a small number, like a fraction, like half, dividing by half is actually going to make it bigger. So that's going to be backwards. So again, small numbers, if you use small numbers and you multiply by a small number, less than 1, It's going to take the function and it's going to stretch it out and make it bigger. That's what's going to happen. So let's look at a couple ideas. We got questions with this. Okay, so I want to stretch the graph. I want to stretch it. That's what I'm trying to do. F of x 4 times its normal width. What value should I use for c inside? So I want to do a horizontal stretch, right? So I want to do 4 times its width, so I want to stretch it. And I want to stretch, so I'm going to put some c inside. Well, if I want to stretch it, I need to use small numbers, numbers less than 1. So I'm going to use a small number. So what small number is going to stretch it to 4 times? Well, I'm actually going to use, c is going to be 1/4. Well, why 1/4? Well, because if c is 1/4, and we try and do this by dividing everything by that c, so we divide by c. If you divide by a fraction, remember how we divide by fractions? Well, we divide by fractions by flipping them over and multiplying. We multiply instead of divide. And so the dividing by 1/4, when you flip it over, you turn it into multiplying by 4. This is multiply by 4. So whatever number is on the bottom, that's what you're going to end up multiplying because it's going to go on the top. So if you want to stretch it to 4 times its width, you put a 4 on the bottom. If I want to stretch it to 5 times its width, I put a 5 on the bottom. Because when I take that and flip it over and multiply, that bottom number is what I'm going to end up going on top and multiplying by. So that the reciprocal is the fancy name for when we flip it over like that. You know, examples for this would be like if you had the square root of x over 4. A lot of times when you want to put a 1/4 times something, you just write like this because you can just do the 1 on top times the x. So it'd be the same thing as you had 1/4 times x. You might just write x over 4. You could have an absolute value function, you know, and you could do it the other way. You could put 1/4 x, and that's okay. So it works either way, but you'd see it both ways. You got a squaring function, so you take x squared and you just put x over 4 and square it like that. So again, because we're putting it on the insides of the square, and we're multiplying by 1/4, this is actually going to stretch this to 4 times this big. It's so weird that you're multiplying by a fourth, a small number like that, and it actually makes it bigger. I had a type of my notes down, so I had to fix this one, so that's why it's like that. But okay, so this one, we had this function, y equals 1 over 3x, and we got that by doing what to the graph of 1 over x. So of course the big difference here is the 3. So we look at this and see in the bottom of the function, with the x, we see a 3. Since it's in the bottom there with the x, it's like we took the x and multiplied by 3. So if you multiply by 3 inside, what's that do? Well, remember, when you use a big number, it's going to shrink it. So this one is actually going to be horizontally shrunk. So this one's horizontally shrunk because sorry, there's a bug on my glasses. That was not fun. Okay, that's horizontally shrunk because we multiplied by 3. We horizontally shrunk it, and by multiplying by 3, we actually shrink it by 1/3. We're actually going to divide by 3. And when you divide by 3, it makes things 1/3 as big. So, divide by 3 is the same thing as multiplying everything by 1/3 or making it 1/3 as big. So that's the difference. So again, big numbers inside shrink, small numbers like a 4th inside stretch, and that's the big difference. Again, horizontal is kind of the stuff that always feels backwards. So when it's inside the function that's horizontal, it's going to feel kind of weird or feel backwards of what we're expecting. Okay, those are all the transformations. So we had the vertical and horizontal stretch to the shifts, the translations. We had the vertical and horizontal reflections where we flipped it, and we had the vertical and horizontal stretches and shrinks. We saw that adding and subtracting always does the shifts. It just depends on if it's outside or inside, whether it's vertical or horizontal. Negatives always do the flips. So if you have a negative in front, then that's flipped, or inside or outside. And then the multiplying by the number, don't pay attention to the sign. We're only looking at the number. Multiplying by the number does the stretches or shrinks. Those are the options. Now, so far we've been doing one at a time, but in real life, a lot of times we'll do more than one at a time. So you'll get equations where you have to identify which one's happening. Now, you do have to be careful though, because the things that are happening do have an order. There's actually an order to doing these. If you do these out of order, you can get different final results, different graphs. So this is the order right here. This is your order. Now, thankfully, it's not super hard to remember, partially because you don't have to remember the whole thing. Technically, the order is you do horizontal shifts first, Stretching, shrinking comes next, reflecting is third, and then last is your vertical shift. But I'll tell you, I've never memorized this whole thing. Because you don't need all of it. Actually, all you need to remember is that the horizontal shifts happen first, and the vertical shifts happen last. As long as you get those two aspects of this, the rest works out. The shrinks and reflections don't really ever mess each other up. So it doesn't really matter if you get those out of order as long as they happen somewhere in the middle. So all this we'll just put in the middle and we'll not really worry about the order. So all you have to remember is horizontal shifts first, vertical shifts last. As long as you do that when you're doing these, you'll be good to go. Okay, so let's try some where they're mixed together. Let's do a problem where we have all of them. So they start off with the original graph being just the x squared graph. So that's just their way of telling us what this originally looked like. What did this look like? Well, it looked like that, because that's what the x squared graph looks like. So originally this is the shape it was. And some of my math lab homework questions might have you actually draw that graph in there. They'll tell you if they want that graph as well as your final graph, if you're drawing graphs. But if they do, that's something you can do. Sometimes they'll just want the final graph. Okay, so this is what our graph is. So they took that graph and they did this graph instead. And we're going to figure out the transformations that happened here to make this graph. So I'm going to look at what happened. Well, I'm going to notice that we have a negative out here, outside. That wasn't there, right? That negative's different. I'm going to notice that there's a -1 on the inside. So this -1 wasn't there before. That's new. And there's a -3 on the outside. The squared and the x, those were both there. So they don't do anything. I'm not going to worry about that 2 power because the 2 power was there to begin with. I'm only looking for the things that got added in. Those things are what change stuff. Those are the things that matter as far as like changing how this works. Okay, so first up, I look at the negative on the outside. I say, okay, it's a negative, so I know it's a flip because negatives are always flips. If it's not subtracting or addition, if it's just a negative by itself, it's a flip. And because it's on the outside, it's a vertical flip. So remember, a negative outside is a vertical flip, which again, that means a flip over the x-axis. So a vertical flip is going to take the function and flip it upside down. So over the x-axis. That's one of the things that's happening. I haven't worried about order yet. I'm worried about what happens. Then I'll make sure I do them in order. So the second thing here I see is a -1 on the -1 on the inside. It's subtracting. We know as soon as we see subtraction or addition, remember that that's always shifts. So we're shifting up or down or left or right. It's a subtraction, so we're shifting it. And then we look and see, oh, this one's on the inside. So it's a subtraction inside. And we know the inside stuff always moves it horizontally. Outside's vertical, inside is horizontal. So this is a horizontal shift. And because it's inside, instead of the negative moving us to the negative direction, it actually moves us to the positive direction. So remember the inside is coming backwards. Subtracting actually going to move us to the right one. So that whole inside stuff feels backwards, right? Negative, doesn't that move us left? No, negative moves us to the right, the positive direction. Okay, the last thing we have here is this -3. So -3, here this is subtraction. Again, a subtraction is going to be a shift, we know that. But now the subtraction is outside. It's not inside the power. Remember the square is the power is on the x, so only stuff that has the square power is going to be considered inside. This is going to be outside. So if we subtract outside, then we have a vertical, because outside is always vertical, shift. And vertical shifts actually do what you expect. Subtract 3 does move it down 3. Remember, horizontal, inside stuff's backwards. Vertical stuff always does what you expect. Vertical actually does move up and down. Okay, now that we got those three figured out what they are, let's think about the order. We said the first thing we do is horizontal shift. So my first thing here, this is going to be my first step. I'm going to do my horizontal shift first. Second thing is a stretch, shrink, or reflection. Well, I don't have any stretch, shrink, but I do have a vertical flip. So this is going to be step 2. That's my second step. Last step is going to be your vertical shift. So this vertical shift is going to be our third step. So that's the order I'm going to do this in. So I'm going to think about my original function. My original function looks like this. So I'm going to go ahead and graph this just so we can see what it looks like. So you take your original function, 0 squared is 0, 1 squared is 1, 2 squared is 4. Kind of looks like this. This is just the original x squared function. That's half of the other half. Negative 1 squared is 1. Negative 2 squared is 4. That looks like that. Okay, so that's just the original function. And what I'm going to do with this function, I'm going to do all three things. I have to make sure I do it in order. So I have to make sure the first thing I do is to shift everything to the right one. So I'm going to take all these points and move them to the right one, because that minus 1 on the inside shifts it to the right. So it's going to go to the right one. Second thing I'm going to do, I'm going to flip these upside down. So the points that are up here, I can go down here. So if I take this point, move down here, this point, move down here, this point, instead of being 4 up, would be 4 down. So it'd be all the way down here. This point, instead of being 4 up, would be 4 down. So it would kind of look like this if I flip it over, after I shift it. I forgot to shift it as well. So I should have put them over here. Let's ignore these ones because I forgot to shift it. My bad. So just ignore the scribbles. We'll pay attention to the actual points where they should be. So it should be here. There you go. So it should look kind of like this. I'm not going to draw the whole thing. I'm just going to put the points. Because we still have one more thing to do. The last thing we need to do is shift it down 3, right? So we've shifted it over, we flipped it upside down. Now we take all those points and we move them down 1, 2, 3. So I move down 3 spots. 1, 2, 3. 1, 2, 3. Oh, 3. So go up here. So we have points here, here, here. This one got 1, 2, 3. Here. This one right here is going to go to 1, 2, 3. And it's down there. And so we're going to have a graph that looks like this. It would have been so much better off if I wouldn't put those extra blue dots there. Sorry about that. So, but it's going to look something like this, where it's been shifted to the right, it's been flipped upside down, and it's been shifted down. Again, I'm doing this by hand because I don't have MyLab up and showing them there. On your homework, you'll just be able to use my math lab. A lot of it is just going to be identifying what happened. You should look at the symbols here and say, oh yeah, negative on the outside is a vertical flip. Negative 1, subtract 1 on the inside is a horizontal shift to the right. Subtract 3 on the outside is a shift down 3. And if you can label all those things, typically my stat lab will just like give you the graph a lot of times, as long as you label all those appropriate things. You might have to identify the original graph. Mention, okay, x squared, and this is what it looks like. You might have to graph it. But the idea is you should be able to take this original x squared graph, look at that things that have changed, and get this final result. Now, one thing about doing it this way, where they give you the graph and they give you the equation for the final graph, is you can help yourself out a little bit using your calculator, right? This calculator is made for graphing. So if you want to graph, you can just use the calculator to graph. Now, I will warn you, be wary. Don't just use the calculator to always figure out what the graph is, because they can give you an equation that asks about shifts and stuff. You saw it in the previous problems we did without actually giving you the equation. So you still need to be able to identify these things. So I would use this more as a check. After you've done the problem and you think you know what it looks like, graph and see if you got it right. But don't use it as a way to solve and get the answer, because it's not that hard to write a homework or quiz or test question where you can't use the calculator. So it's a good backup, it's a good check, but it's not a good way to do all your problems. So I'm going to type this in. I type the negative, because it's a negative in front. Make sure you're using the negative button and not the minus button. So negative parentheses, x minus 1. So we use x minus 1. Close that parentheses, and then this is squared. So I'm going to use my squaring button right here, like that squaring button. And then I'm going to take that and subtract 3. Make sure if you use like the power button that you got out of the power, if you do the minus 3, you don't want the minus 3 in the power. So mine's not, so you can see that. So once you've got it typed in, hit graph. It should look like what we got. Yeah, so our final result was a graph that was down and to the right and flipped upside down. And so you can see that, how it's to the right a little bit, shifted over, it's flipped upside down, and you can see it's moved down, right? It's not up here in the middle, it's down 3. So that's what it should look like. So you can double check those with your calculator. But again, don't just expect your calculator to give you all the answers. Definitely know how to do this without the calculator. A couple more examples, and that's it for this section. So a couple more examples. Okay, this graph originally was square root of x. So just show you what this looks like. If you do square root of x, well, square root of 0 is 0, because that's what type of self is 0. 0 times self. Square root of 1 is 1, because 1 times 1 gives you 1. Square root of 4 is 2. I'm not going to do 2 and 3, because the square root of 2 and square root of 3 are not nice answers. The square root of 4 is 2. So we get an answer like this. That's what it looks like. Notice I didn't do any negatives, because you cannot square root a negative, right? So we said the square root function, square root of x, always looks like this, where it starts at 0, because it's the smallest number you can square root. And it's got to go up to the right. It kind of gets flatter as you go, but it never quite gets flat. So it is always going higher and higher forever, but it just kind of gets flatter as it goes. It takes a long time. If you want to get up to like 100, it takes a really long time. I think you have to get like 10,000 before you get to 100. So you go over 10,000 before you can go up 100. So this gets really flat, but it always is going up higher as you go to the right. Okay, that's what the original graph looks like. So that's where we just graph that just to see what it looks like. And then they say, okay, we want to look at this graph. We want to think about the transformations to get this graph. Again, first thing I'm going to do, I'm going to look at what changed. Well, here you can see there's a 2. That's different. And you can see there's a -1. And those are the differences, right? Those are the only things that changed. They added a -1, they added a 2. Each time I'm going to look at what happened, and I'm going to think about what that change does. So this -1 on the inside, right? So you have subtracting 1 inside. Remember that subtracting is always a shift inside the square root, because you see the -1 is inside the square root. So subtracting inside is going to be a horizontal shift, because inside is always horizontal. And then because we're subtracting on the inside, remember that you don't go in the negative direction, you actually go in the positive, because this horizontal on the inside is always backwards. So subtracting 1 on the inside is actually going to go to the right 1. So no, minus is the left direction, but with inside stuff, you always go the other way. So instead of going to the left -1, we're going to go to the right 1. So that's what the -1 does. How about the 2? Well, the 2 is a multiplication, so it's actually a stretch or shrink. Because it's on the outside, it's a vertical. So multiplying by 2, which is bigger than 1. That's what's important about it. 2 is bigger than 1. Outside, well, we know it's going to be vertical. And because it's bigger than 1 on the outside, big numbers on the outside are stretches. So it's a vertical stretch by 2. It's going to make everything twice as far from this x-axis. We're going to stretch it out vertically. So you think of this like x-axis as your middle, and think about stretching out vertically. So it's going to be taller than it would have been. It's going to be steeper, because we never said those infinitely tall things, they just get steeper. Okay, so I think about doing these 2 transformations. I got to make sure you do them in order. Like I said before, we always start with the horizontal shifts first, right? Horizontal shifts first, and we do the vertical shifts last. Well, we have a horizontal shift, so that would be our first thing. We only have 2 things, so the other one has to be our second. It doesn't matter what it is, because we always do horizontal shifts first, and then anything else. So again, you see, I don't have to remember everything memorized. As long as you remember that horizontal shifts first go first, and vertical shifts go last. As long as you do that, you're pretty good off. Okay, so we've got to do our horizontal shift first. So we're going to take all these points, we're going to move them to the right by 1. So that's where they would end up. So if we did the shift, it would look like that. It would have a line. It would just be over to the right 1. This whole thing would just be over right. It wouldn't have a value over here anymore. Then we're going to do a vertical stretch. So again, we're moving everything further from 0. We're spreading it out. Well, 0 doesn't go anywhere, right? Because if you stretch 0 times 2, we get 0. It just stays where it is. Stuff in the middle just stays where it is. But this point that's 1 high is going to get stretched up to being twice as high. So it does go up like that, and now it's twice as high because it's going up. This one that's at 2 is going to be twice as high. Well, twice as 2 is 4. So it gets stretched up as well. And so it actually ends up looking like this. So you can see it's still flattening out, but it started a lot steeper because we stretched it upwards. And so this is what that g of x function they have up there, this guy, 2 times root x minus 1, this is what it looks like. Because again, the 2 stretched it upwards, the minus 1 shifted it to the right. And that's what the final result would look like. Again, you could throw it in your calculator. I'm not going to just because I think you guys got the idea. But the big thing is you need to be able to identify those transformations. Okay, I got one more. This is kind of an interesting base teaser one. And then after that, we're done. So find the equation of g of x if it's obtained from transformations of f of x, which is x squared. So they're saying this guy right here is f of x. This is x squared. And this is g of x. And so they want to find the equation. So that's a big difference here. We're looking for the equation. We're not trying to write the graph. We're trying to find the equation of this guy by identifying the transformations that went from here to here. So how do we get from here to here? By identifying those transformations, we should be able to write the equation for this thing. So I go to look at this and think, okay, what happened? Well, a few things happened. One thing that happened is you can see that it's moved to the right. You can see I had a point here, but it's moved over because now it's to the right one. So it is shifted right by 1. Well, what do you do to shift it right by 1? Well, to shift it right by 1, remember that's going to be a horizontal shift, so that's going to be a inside thing, right? So this is inside. And to make it go to the right, we have to subtract 1. So we're going to subtract 1 inside. Doing that will make it go to the right one. So that's how we do the first thing. So we're going to have to put some kind of subtract 1 on the inside, and that will give us that shift right. Next thing you'll notice, of course, it is flipped over this x-axis, right? Instead of going upwards, it goes downwards. So it's got a vertical flip. Remember, we'll say, the textbook will say it's flipped over the x-axis, because it's flipping over the x-axis, so you're flipping up and down over the x-axis. And we said vertical flips, vertical stuff always comes up from being outside. So this is going to be a negative outside. That's how we're going to get that. So when we draw this, we write the equation, we're going to have a negative on the outside. But one more thing, you'll notice that, yeah, it's flipped over, but it's not this high anymore. It got moved down to, so it actually is shifted down to. So we do need to shift down by 2. Vertical shifts, shifting up and down, remember on the outside. And to go down by 2, vertical, you actually do what you expect. You just subtract 2. So this one is going to be subtracting 2 on the outside. That's what this one's going to be. So we're going to have to subtract 2 on the outside to move it down to. Okay, now put that all together with our original x squared, and we got an equation. So to get this equation, I'm going to call this g of x, right? That's the function. So we call this g of x. So g of x, it's going to have an inside. So remember, to get x squareds to have insides, we're going to put parentheses, put the square on the outside. So now that's inside. X, of course, has to be on the inside. The other thing that has to be inside is subtracting 1. So we're going to subtract 1 on the inside, because that subtract 1 on the inside is going to be the horizontal shift. That's what's going to move to the right. Next thing we need a negative on the outside. We're going to put a negative on the outside, because that negative outside is going to take this and going to flip it upside down. Last thing, we need to subtract 2 on the outside. We want this to move down 2. So we put a minus 2 on the outside, and that moves the whole function down 2. And that is our equation. G of x is going to be this equation with a negative, it's in front of the parentheses, x minus 1 inside the parentheses squared, because it was a squared to start with, and minus 2 to shift it down. So that's the transformations that occurred, and that's how the equation would look. So you can actually use this. Hopefully you can see how powerful this is, that if you get comfortable with these transformations, you can take equations and just dissect them, compare them with the basic version of the equation, and you can actually see what the graph looks like pretty easily just by looking at the transformations once you get the hang of it. This is something that we will see throughout the semester. We're not going to cover it super heavy later on, but it will pop up here and there. We'll see other types of functions that we haven't covered yet, even beyond what I showed you. And so those ones, when we see those, we'll always talk about what the transformations are. So you'll see transformations pop up even beyond this exam. So that's it for outcome 11. Again, this is our last outcome for the unit 1. So at this point, you should be finishing up this homework and then getting ready for the exam that's coming up soon. So good luck with the exam, and I will see you on the next set of notes.